So let's start today's session. So we are going to discuss the get problems based on this topic series in shunt compensation and electric field distribution insulators, distribution systems and per unit quantities. Before we are going to solve the problems, just we quickly go through the some expressions that will be helpful in solving the problems. So if we want to derive the power flow equation in transmission lines, then the expression will come out as like this. For the sending end, I have write it down for PS and QS. So as we know that transmission line is characterized by the ABCD parameters, and this two bus system having bus 1 and bus 2 mentioned, and the voltage as bus 1 is Vs at the angle of delta, this is power angle, and at the voltage at the bus 2 is Vr at the angle of 0 degree. Correspondingly, this active and reactive power present at the bus 1 is represented by Ps and Qs respectively, and the active and reactive power for the bus 2 is represented by Pr and Qr. So this is the expression we will get after going through the calculation, some calculation. So don't there is no need to remember this expression. This is little bit complex, and even the in GATE exam it is not important for our exam. So this is generalized expression, both active and reactive power for the sending into transmission line. And as you can see that for active power, the cos expression will come, and for the reactive power, just there is difference in sign term. This cos term will be replaced by sin term, and there is no difference in these expressions. And this it is also important that alpha is the angle of this parameter A, and beta is the angle of parameter B. So alpha and beta are used in these expressions, and delta is the power angle, the difference between the sending end voltage and the receiving end voltage. And now we can also write the active and reactive power for the receiving end of transmission line, PR and QR. Therefore, we can say that real and reactive power line losses will be PS minus PR. This is the real power loss, and the Q loss will be the reactive power loss. This is important, and this will be used in our problems. So these are the generalized expression for the active and reactive powers at the sending end of transmission line and receiving end of transmission line. Now we will see the expression for short transmission line. For a short transmission line, we know that this A is equal to D is for every type of transmission line, but this one come is equal to 1 at the angle of 0 degree for short transmission line, and we can represent Z at the angle of theta, and C will be 0 for short transmission line. So if we write the if we convert the previous expression for short transmission line, then we have to substitute alpha is equal to 0 degree and beta is equal to theta, and B is replaced by Z. So these quantities we just put in the previous expression, we will get the active and reactive power at the receiving end like this. Vs for active power at the receiving end will be Vs Vr divided by magnitude of Z cos theta minus delta minus Vr square divided by magnitude of dash cos theta. Similarly, Qr just replacing cos with sine, then we will get the reactive power. And for the sending in power, just this term will come first, like this expression. this expression will come here first. Just to go through this expression, you will easily remember this expression. Now this is for short transmission line. Now again, if we want to just concise this expression that will be mostly asked in the competitive exam, then we derive this is for lossless transmission line. These all expression are for lossy transmission line. But if we want to derive the expression for lossless transmission line, then we have to substitute r is equal to 0. R is equal to 0 means you will get theta is equal to 90 degree, and z in z expression x only will comes. So we can write the transmit we can just represent the two bus system like this, and putting this theta is equal to 90 degree, we will get PS, that active power at the sending end and active power at the receiving end will be Vs divided by VR x sine delta. So active power at the sending and receiving end will be equal. That means there is no loss happening in the transmission line. And for the reactive power, Qs will be Vs square divided by x minus Vs Vr divided by x cos delta, and Qr will be Vs Vr divided by x into cos delta minus Vr square divided by x. So these three expressions is very important for competitive exams and very important for our GATE exam also. These expressions might comes into other means uh, means, like other like electrical machines and power tonics might be this can be used, but power system, the most network, in network you can also see this type of expression. So please remember these expressions. Now we are going to solve the first problem of today's session. So this is the first problem, and the question is that consider the two bus power system network with given loads as shown in the figure. All the values shown in the figure are in per unit. The reactive power supplied by generator G1 and G2 are Qg1 and Qg2 respectively. The per unit values of Qg1, Qg2 and line reactive power loss respectively are. So this problem has been asked in GATE 2018, 2 marks. You just also solve parallelly with me. So what as we can see that in this problem, at G2 load demand power is load demand power is 20 per unit, while G2 is providing only 15 per unit. So the remaining power comes from G1 only. So we can write that at generator 2 side, load demand power is 20 per unit, while G2 is only providing 15 per unit power. So the remaining power will comes from so the remaining power comes from G1, and this is also lossless transmission line, so we can directly write that active power at the sending end of transmission line will be both will be equal. P1 is equal to P2 because there is no loss in the transmission line, so it will be V1 divided by V2 divided by X sine delta, V1 into V2 divided by X into sine delta. So as we know that it will be 5, then V1 is 1 per unit and V2 is also 1 per unit. X is 0.1. We take the magnitude of X, and from here we will get the delta value. So sine delta will be 0.5. Therefore, delta value will come as 30 degree. So now we can find the QG1 by getting the Q1 value and Q2 value, that is reactive power at the sending end of transmission line and the reactive power at the receiving end of transmission line. And just subtracting both these terms, we will get the Q loss. So now reactive power at the, you can represent this as bus 1. Reactive power at the bus 1 will be Q1 is equal to V1 divided by XL, as we have seen the expression in the last slide, V1 divided into V2 divided by X cos delta. So all the values are known. 1 square 0.1 minus 1 into 1, X will be 0.1 cos 30. So this will come as 1.3397, approximately is equal to 1.34 per unit. And now for the reactive power at bus 2, reactive power at bus 2, we know the expression will be a square term will go to the right side, and this side will, left hand side will be V1 into V2 divided by X cos delta minus V2 square divided by X. We can see that in reactive power expression, a square term will come in at where we are finding the reactive power. If you are finding the at bus 1, then a square term of voltage will be V1 square. And similarly for the reactive power at bus 2, a square term will be for the voltage at the bus 2. So this is trick for remembering the reactive power expression. Don't confuse with Q1 and Q2. Cos 30 minus V2 square divided by 0.1. This will come as minus 1.34 per unit. So as we have seen that what is the line reactive power loss? Line reactive power loss, that is Q loss. Q loss will be Q1 minus Q2. Means whatever the reactive power present at the difference of reactive power present at sending in and the receiving in. So sending it we are having 1.34 per unit minus, and receiving it will be 1 minus 1.34 per unit. So this will be 2.68 per unit. So one answer we got. Now for finding the QG1 and QG2, what we will do? So at bus 1 we can write that reactive power being provided by generator 1 is equal to load reactive power plus reactive power present at the bus 1. So we have Q load is 5 per unit plus Q1 will be 1.34 per unit. So it will be 6.34 per unit. And similarly for QG2 at bus 2 will be, so QG2 will be what? Q load minus Q2. Sorry. Reactive power being provided by generator will be Q load minus Q2. So this is 10 minus 1.34, that will be 11.34 per unit. So as we see from the options, C is the correct answer. Till here, is there any doubt?
Yes, sir.
Yes, tell me.
Uh, Sir, show me previous slide. Sir, reactive power at the load bus 1, Q1 equal to V1 is divided by XL minus V1 V2 divided by XL cos theta. For in reactive power at bus 2, Q2 V1 V2 divided by X cos theta. Sir, in this term, the cos theta, second in the second one, cos theta is uh, come first and second in first equation. There
Yeah.
is cos theta is in latter term. Why?
Yeah. Because this expression we have seen like from this for short I we have you can derive this expression like for a short transmission line, this you generalized expression, and then you will find for lossless transmission line, then you will get this expression.
Okay, sir.
So it then means this expression is comes from mathematically. You don't need to put means logic. So this second expression is also based. Second problem is also based on the expression we have just learned. So this problem is that bus 1 with voltage magnitude 1.1 per unit is sending reactive power Q1 to towards bus 2 with voltage magnitude 1 per unit through a lossless transmission line of reactance X, keeping the voltage at bus 2 fixed at per 1 per unit, and magnitude of voltage at bus 1 is changed so that the reactive power Q1 to sent from bus 1 is increased by 20%. Real power flow through the line under both the condition is 0. The new value of the voltage magnitude V1 in per unit at bus 1 is. Just note down this problem and we will solve it. So now we are going to solve, and you just also try to solve. And whoever is getting answer, type your answer in the chat box. So in the at the starting, we are having given the magnitude V1 is equal to 1.1 per unit, and sending reactive power towards bus to with voltage magnitude V2 is equal to 1 per unit through a lossless transmission line having reactance X, and keeping the voltage at bus to fixed at 1 per unit. So correspondingly, magnitude voltage bus is changed. So now we will just uh, look into the expression. Since active power expression will be V1 into V2 divided by X sine delta, and in both condition active power will be 0. So we can say that delta value is 0 degree. Now we can write the expression of Q1 to how you can write V1 square divided by X minus V1 into V2 X cos delta. So Q1 you can write V1 is 1.1 square minus X 1.1 into V2 is 1 per unit divided by X cos delta 0 means 1. So 1.1 square, that is 1.21. 1.21 minus 1.1 divided by X minus 1.1, this will come as 0.11 divided by X. Now what the reactive power sent from bus 1 is increased by 20%. So new reactive power is Q1 2 dash will be 1.2 Q1 2, and in this case voltage at bus 2 remain fixed at per unit while the magnitude of voltage at bus 1 is changed. So let us V1 dash you can assume, and V2 is same, that is 1 per unit. So what will the expression? That will be V1 square divided by X minus V1 divided by X, and in this case also delta will be 0. So this is the expression you will get, and just put this Q1 value, then you will get 1.2 into 0.11 divided by X is equal to V1 square minus V1. So on multiplying with 1.2, you will get 0.132. This will get cancelled out. So 0.132 V1 square minus V1. So on solving this quadratic equation, V1 square minus V1 minus 0.123 is equal to 0. So in the GATE exam, you have to use this expression. Minus B 1 plus minus B square 1 plus B square minus 4AC 0.132 divided by 2A. So V1 dash value will come from here 1.12 per unit or 0.12 per unit. So which value we will take? 1.12 per unit or 0.12 per unit? Hmm? Anyone can tell? So there are two values you will get, V1 dash 1.12 per unit or
0.12 we consider. 0.12.
why?
Smallest value is the
Why?
smallest value we consider, sir, in general.
Any other one? We cannot take this 0.12 per unit. We have to take 1.12 per unit. Why? Because you can see that V2 value is fixed at 1 per unit, right? And in first case, V1 value is 1.1 per unit. And as we know that reactive power flow depends on the voltage mismatch, and this reactive power is increasing, is increased by 20%. So reactive power always flows from the higher magnitude voltage to lower magnitude voltage. So if it is increased only, then the reactive power flow will be increased. Q12 will be increased. Suppose if this is lower, if V2 magnitude will come as lower than 1 per unit, then this reactive power flow from this V2 to V1, from bus to bus 1. So that is the concept. And in the power system, one thing also remember that most of the answer will come, if any changing is there, most of the answer will come just near to the voltage. Like if voltage at bus 1 in per unit given approximately 1 per unit, then the voltage at other bus it will be approximately like there will be zero point 0.3 or zero point 0.4 maximum deviation. So there is not a significant deviation. So this 0.12 per unit is very large deviation from the bus 1 magnitude. So you cannot take this 0.12 per unit. And other thing is that you just go through this like reactive power flow happens from higher voltage magnitude to lower voltage magnitude, and active power flow from the higher angle to the lower voltage angle. So this is the thing. So answer for this problem is 1.12 per unit. Now let us see the third problem. Third problem is not we require the expression we have learned. This expression is this is a very simple problem and based on the power factor correction. Third problem is that a load is supplied by a 230 volt 50 hertz source. The active power P and the reactive power Q consumed by the load are such that the limit for the active power is 1 kilowatt and 2 kilowatt, and for the reactive power it is between 1 kVAR and 2 kVAR. A capacitor connected across the load for power factor correction generates 1 kVAR reactive power. The worst case power factor after power factor correction is. This is a very simple problem and it has been asked in 2017, 2 marks problem. So just you all of you try this problem, and this question 2 is asked in 1 minute. GATE 2020. So we can assume that one generator is having like it connected to a bus, and where this reactive power compensation happening, and this QC is 1 kVAR. So the active power P and the reactive power Q consumed by the load. So here you are having load SL PL plus JQL, and this generator you can take SG PG plus JQG. This is being supplied. So the worst power factor after power factor correction, and it is the just you need to take care of the limit only. So if you draw the power factor triangle, so it will be like this. So this is the angle phi, and we are having active power this side, and this is PG, and you can take this QG. QG will be what? QG will be Q load minus QC, right? And PG PG is equal to PL. So uh, so the the reactive power, so the cosine of angle power factor will be, cosine of the angle will be cos tan inverse this Q max divided by P minimum. Why I have taken this Q max and P minimum? Because you need to find the worst power factor. Worst power factor means this Q maximum will be high and P should be minimum, so that you will get this angle much higher. Phi will be get much higher. Like if phi increases, then cos phi will.
0.447 lakh, sir.
No, that
Uh,
is incorrect. Try again. It will come 0.707 lakh. Now you can see what I am solving. you did little bit mistake in taking the active and reactive power limit. What you have to take the active and reactive power. So this if you increase the phi, then power factor will decrease. That you have to you have to find out. So how you will increase the phi? So phi will increase by taking the higher magnitude of reactive power and lowering this active power. So that's I written Q max divided P minimum. So how this Q maximum?
More, more reactive power consumption means worst power factor.
Yeah, right. And active power should also lower for generating by this generator. So here the active power limit is 1 kilowatt and 2 kilowatt. So you have to take not 2 kilowatt, 1 kilowatt. Then you will having get the higher value of angle, and this power factor will more worsen, and power factor will, means much lower. So that mistake you did. You have taken this active power as 2 kilowatt. Other things for other things you did fine. So Q max will be what? Q max you take just QL is equal to 2 because you cannot change load. QL will remain same maximum, and then minimum value will be this QC is 1 kVAR, so 2 minus 1, and P minimum will be what? P minimum, and this you have to take 1. Then cos tan inverse 1.
Got it. 0.707 lakh.
Yeah, 0.707 lag.
Here 2 max means 2 minus 1, sir. 2
Yeah,
max.
means
Why?
for you can more specifically write QG max means generator reactive power being supplied by generator.
Sir, I have one doubt, sir.
Yeah,
Can you clear why, sir, 2 max is nothing but 2 minus 1?
because QG max will occur at what reactive power. If you have taken load reactive power at 1 kVAR, then it will be 0. So you have to take the maximum value, this 2 kVAR load reactive power. So 2 is the QL, QG maximum is the, you can also write QG maximum is equal to QL max minus QC, right? So QL maximum will be 2 and QC is fixed. It is fixed, so you cannot change this. So QC is fixed, so 1 minus 1, this is QG max. And you have to take PG minimum. If you take PG maximum value, then it will having more power factor than this value. So you have to take PG minimum. PG minimum will be
Got
like
it, sir. Yeah.
PL is equal to 1. So
Thank you, sir.
if,
Got it.
okay, fine. So if there is no doubt, we can move to another problem. What is the time? So we have 20 minutes more time. So this is a very simple problem and you have to just apply the KVL, and this is a little bit older problem. It has been asked in GATE 2014. These type of problems you don't need to remember any expression. If you having good hand in this practicing problem and solve problem, then you can easily solve this type problem. So the problem is that a distribution feeder of 1 kilometer length having resistance but negligible reactance is fed from both the ends by 400 volt 50 Hz balance sources. Both voltage sources S1 and S2 are in phase. The feeder supplies concentrated loads of unity power factor as shown in the figure. The contribution of S1 and S2 in 100 ampere current supplied at location P respectively are. So we have to find this contribution from S1 and S2 in 100 ampere current supplied location P respectively.
And both sources fed the same voltage 400 volts. So difference of voltage is zero, sir.
I didn't got your point.
S1, yes, S1 voltage is 400 volts. S2 voltage also 400 volts.
Yeah,
So the potential difference is zero, sir. Current is zero.
how is this? You have, but in meanwhile, this at nodes the potential difference is not zero, na. That is the thing.
Uh, not node P, sir. 0 and 100 amperes. Our answer is 0 and 100 amperes, sir.
But
You can
first,
answer. I
first
will ask
we'll
later.
see the solution, then you can ask. So let we assume that resistance of line, V R ohm per kilometer. So if you want to make the equivalent diagram for this circuit, for this bus, for this two generator distribution system, then you can make like this, as he is saying. This is 400 volt 50 hertz. So this is resistance. You you take it as 0.4 R, and here it is having 200 ampere. And again this is 0.2 R. So here it is taking 100 ampere. So it is 0.2 R, again 200 ampere, Vs1, and this is 0.2 R, Vs2. Both are equal, right? So it will get cancelled out. Suppose this is I current being supplied by Vs1. So this will be I1, you can take. This will be I1 minus
200,
200. Similarly, this is I1 minus
300,
300. Similarly, this one is I1 minus
500.
500. Now we apply the KVL. So applying KVL is equal to Vs minus I1 into 0.4 R minus I1 minus 200 into 0.2 R minus I1 minus 300 into 0.2 R minus I1 minus 500 into 0.2 R is equal to Vs2. So both will cancel out since both are equal. So it will be minus 0.4 I1 R minus 0.2 I1 R plus 40 R minus 0.2 I1R plus 60R minus 0.2 I1R plus 100R is equal to 0. So R will be just taking common minus 0.0.6 0.8 minus 1 minus I1R is equal to minus 200 R. So R will get cancelled out, so I1 value will be 200 ampere. So this value will be 2 ampere. You have to find this at node P. So actually from here this will be 0 ampere coming. So from this side will be minus 100 ampere. So from this side will be 100 ampere. So this is correct answer will be D. This is a little simple problem. So is there any doubt? So let us move to the last problem of today's session. This one is a little bit good problem and is recently asked in GATE. This problem is from GATE 2021. So the problem is that in the figure shown, self-impedances of the two transmission lines are 1.5 J per unit each. Self-impedance. So XS1 will is 1.5 J and XS2 is J 1.5 and Jm is 0.5 J per unit is the mutual impedance. Bus voltages shown in the figure are in per unit. Given that delta is greater than 0, this is greater than 0, the maximum steady state real power that can be transferred in per unit from bus 1 to bus 2 is. So for solving this problem, first you need to find the equivalent reactance. So first if you will find the equivalent reactance, then you can apply this maximum steady state real power. So as we can see that this is parallel inductors connected having this additive polarity. So you need to uh, remember the expression, what expression you need to for the additive polarity and subtractive polarity. So I have noted down here. So if you are having series connection of inductors and between the inductors additive coupling is there, then equivalent inductance will increased. So L equivalent will be L1 plus L2 plus 2M. This is for equivalent coupling. How you determine equivalent coupling? Means both at both dots current is coming. Means in both dots current is entering. And subtractive coupling, how you can define? In subtractive coupling, in one dot current is entering and another dot current is leaving. So this is equivalent impedance, equivalent inductance will lower down. So L1 plus L2 minus 2M. Now we will see the parallel connection of inductors. For parallel connection of inductors, if we are having additive coupling means currents are entering the dots similar way. Like in both dots, the currents is entering. So this is additive coupling, and the equivalent inductance will be more. So L1 L2 L1 into L2 minus M square divided by L1 plus L2 minus 2M. This these all the expression are very important for series coupling and for series connection and for parallel connection. And now for subtractive coupling I did here wrongly. This is not dot, here it is dot. So in one dot current is entering while in other dot current is leaving. So this is subtractive coupling and equivalent inductance will lower down. How you can compare? because here you can see that denominator is higher than the previous one, so the equivalent inductance will lower down. So that is the property of subtractive coupling. Now we will use this
Yes.
subtractive coupling, sorry, this additive
In
coupling, because in this
in
question,
a different
yes,
x equivalent to 1, sir. X equivalent to 1
yeah, very
in this
nice. So the correct answer will be one. What is your name?
Veeraya, sir. Veeraya.
Who told the answer?
Me, sir.
Okay,
Myself, Veeraya.
okay, nice. Very here. So, so solution for the problem will be, we are having given values are xx1 is equal to j 1.5, xx2 is equal to j 1.5, xm is j 0.5. But whatever the formula, we know that L equivalent for additive coupling is L1 plus L2, sorry, L1 L2 minus m square divided by L1 plus L2 minus 2m. So you need to first convert this into x equivalents. How we will convert x equivalent? Just multiply with omega square both side. Omega square L1 L2 minus omega square m square divided by omega square L1 plus omega square L2 minus 2 omega square m. So take the omega L1 omega L2 minus omega m whole square. Take 1 omega common, then you having omega L1 plus omega L2 minus 2 omega m. So take this omega this side, you will get expression x equivalent will be just similar to this one, x1 x2 minus xm square, xm square divided by x1 plus x2 minus 2xm. Just similar expression of reactance with the inductance value. So put all this value, you will get the x equivalent. X equivalent will be x1 x2 minus x m square divided by x1 plus x2 minus 2xm. So this is x equivalent will be 1.5 into 1.5 minus 0.25, 1.5 plus 1.5 minus 2 minus 2 xm. Xm will be 1, there will be 1. So this is 2.25 minus 0.25, 3 minus 1 2, so upon 2 by 2 1. Therefore maximum, in this question it is asked that maximum steady state real power deliver, maximum steady state real power can be transferred will be, so in this sine delta will be 1, so p max will be mod e mod v divided by x equivalent. So x equivalent is 1, so mod e mod v is the answer. So A is the correct answer. So this expression comes from here, mod D mod V divided by x sine delta. So for P maximum, you have to take the delta is angle is 90 degree, sine delta will be 1. So that's all for today's session. We will solve more problems in the next session. Thank
Thank you,
you.
sir. Can you share today's PPT, sir, through
Yes,
chat box?
PPT, you can go through the YouTube channel, or it will be come in some days on the Gate portal also.
Okay, sir.
Do you have access? Uh,
If you possible, please share this PDF to chat box, sir. Google Drive link.
yes, I already shared for both the previous one. This
Okay,
one
sir.
will also
Okay.
share. You know how to
Okay.
access that, I think.
Oh,
Biray?
yes, sir. Yesterday, oh, yes, sir. Yesterday also, mentor shared it, sir.
Okay, that's good.
The um,
Okay.
PPT today class PPT. Please, please create Google Drive link, sir.
Okay, that I will share in this Gate portal also. That is fine. I will share
Your
that.
YouTube channel you can share there also.
Yeah, yeah.
I have already.
There I also put. That's just like similar way.
Will you put it today?
Yeah, in the night I will put.
Okay, okay. Fine.
Okay, Bill. Nice for attending the session. We will meet on the next Saturday. Thank you, everyone.
Okay, thank you, sir.
Thank you, sir. Very informative section, sir.